Okay, we can get started. So last time we spent two lectures talking about caches and talk about how the cache is internally organized and talk about how cache writes is handled different write policy. So in cache 3, we're going to focus on cache coherency. And we already talked about cache coherency in GPU architecture, but for GPU architecture, cache coherency is much easier because we simply do not care that much about cache coherency. Cache coherency is achieved by flushing back into the memory. Then today we're going to talk about cache coherency, and our coherency is mainly for CPUs. And we really care about if we want to read some data or write some data that we do not have problems that always get to the correct result. Okay, so today's content is mainly comes from this book. It's not from the textbook or syllabus, but from this book. This is actually a very good book. It's the classic tutorial for memory consistency and cache coherency. So we're not going to talk about memory consistency, but we're going to focus on cache coherency in this in our course. Okay. Then for cache coherency, we're probably only going to spend this one lecture, and then probably we'll talk a little bit in the next lecture, but that's for one lecture, that's in general good enough to give you a understanding about how coherency works. Then for cache coherency, I always have a feeling that for one lecture, it's definitely not good enough for you to understand everything. Then like when in my mind, when I know, oh, I actually know everything about how cache coherency works, when I try to implement cache coherency protocols in a simulator, I always find there's so many things. There's so many detail, 1 or 2 cycle difference, how to handle this type of difference is there different internal state or transient state, how we can handle those cases. Okay, so during one lecture time, I can only give you a very high-level introduction to how general things work. And there are different type of caches, write through, write back, write evict, write around, and how to support those things are something that you can think about when you really need those things. Okay, so we start by talking about cache hierarchy. Then you're not familiar with this cache hierarchy. So we talk about in GPU architecture, cache hierarchy. So at the beginning we talk about the core and the DRAM, right? But for cache coherency, we always talk about multi-core problems, or at least there are multiple caches that are involved, multiple caches at the same level. So when there's a DRAM, when there's only one unit, there's no problem at all. When there's only one DRAM, there's no problem at all. But after we insert caches, we insert L1 caches there. Like for example, here, these L1 caches, we typically call them core side caches in GPU terminology, right? The core side caches, then we start to have cache coherency issue because this L1 cache and this L1 cache will have a different version of the data. Then in some organization, these L2 caches are organized in this way. These are still useful because these L2 caches can be larger, but have more distance from the core so that it can have larger space, but slower memory access time, more latency. But this is not a more general case. A more general case is more like this. So L2 caches is shared by some cores. I'm still not talking about it's a memory side cache because you will see how L2 scales as we add more cores. But this L2 cache is shared by a group of L1 caches. And this makes cache coherency problem even more complex. Then let's look at this. If you have a 4-core system, it should be core 3 and core 4. If you have a 4-core system, each core may have a private L1 cache, right? So it's dedicated access, the fastest speed that we can get the data. And there are larger L2 caches that are somehow shared by a cluster of cores. So if you look at this L2 cache, only look at this L2 cache, then consider the effect of core 1 and core 2. So core 1 and core 2 can both be friends and enemies. Like when they are friends, say core 1 may access some piece of data, then core 2 may access the same piece of data, the same cache line. In that case, core 1 may read the data for core 2 so that core 2 may reduce the memory access latency, right? Now, on the other side, they can be enemies, so they can stretching each other. So for example, core 1 and core 2 are accessing totally different data. Then they may access totally different data, but they need they both need access relative large range of data. The core 1 will load the data, then to evict the data that is loaded by core 2. And core 2 is also loading data that is for the data that is evicted by core 2 is loading data and evicting data loaded by core 1, right? So they are thrashing each other. Now making none of them can get data. Both of them need to go to the DRAM to access data. So this type of relationship, it can be very complex when we're talking about cores sharing caches. So then we talk about cache coherency and first look at the interface of cache coherency and how we define cache coherency. So in a cache system, we consider a cache. There are two caches, two same level caches, and the interconnect that is in between. So we only, for simplicity, for teaching purposes, we only consider one level of cache. So these caches are connected to a DRAM, and at the beginning we only consider two caches. Okay, you can consider this DRAM or this memory as just another level of cache that is managed in another way. But in reality, if you consider multi-level of caches, things can be more complex than a single level of cache. Okay, so say if both of the caches, both of cores wants to read the data, then there's no problem. Then we can simply duplicate this piece of data to both sides. Then they can keep reading this data. So if you have data reading, if you there are read only data, you can duplicate as many shares as possible, and there's no problem, right? But once you have write data, if this side wants to write data and this side wants to read the data, there's a problem because you are expecting you should always read the most recent version of the data. Now, in this case, you are reading the wrong data, right? So there is a little bit peeking into the memory consistency part. So memory consistency part, there are different type of consistencies. For example, if we read, so for some different definition for consistency, if we read the data, we read a wrong data. This may be okay for some time, but eventually we need to read the right data. For example, on one side we say, wait until A equals to 42. On B side, we start to write into the increment A until 42. So it's okay that for some times A is not reading the most up-to-date data, but eventually it has to arrive at this point. If you don't have anything that can evict this part of data and get the newest data, then this core may get stuck by that point. But this is not strictly a memory consistency definition. For memory coherency, we're always talking about one particular cache line. What are the behavior that when we're accessing one cache line? Now for memory consistency, we're talking about different cache lines, different addresses. So if I write one thing and write another thing, there must be an order. Say write A happens before write B. Then this write order, what's the observation like from the perspective of another cache? It does from another core, does the other core may observe around the other direction of write, right? Read and write orders are the things that really matters in memory consistency. But here we're not talking about memory consistency. We're talking about cache coherency. So in the domain of cache coherency, we only want to read the most recent data. Okay. So in this case, we consider this is a mistake. This is a arrow that we cannot allow these things to happen. So what are our definition for memory consistency or cache coherency is we only consider these cases. So it's called a single writer, multiple reader style of coherency. So we're talking about for any given memory location. So we're only talking about one particular or each particular memory location. And typically we're talking about cache lines. Now for any moment in time, now we're talking about a moment. So how to understand this moment is a little bit hard. Is there's no clear definition. It's not a cycle. Okay. We typically call it an epoch. It's more like a logic time. A logic time means when this part writes, when this part of writes data, and when this part needs to read the data. The time between this write and this read are considered an epoch. Okay. So this is a pure logic concept that you cannot really say, oh, how many cycles is an epoch? Here, there's no clear definition. It's in terms of logic that another read or write event happens. Okay, so within one epoch, we can allow two cases. Either a single core, it's just one core is writes to it, or some other cores may, or some number of cores may read it, right? So we can have a limited number of cores that are reading this data, or we can have a single core that is writing to it. So this defines what are allowed, right? So what are not allowed is more than one core is writing the data, or one core is writing the data, but other cores are still reading from it. This is something that we do not allow. Okay. So in one logic time period, we can only allow either one core is writing data, or some cores are reading the data. Some number of cores are reading this piece of data. So read and write should never overlap in terms of our logic time. Okay. So we should exclude, we totally separate read and write. So, so there's a definition here is for a given memory location. We have already talked about epoch, right? Then for a granularity, for the other part, the memory location, then we can actually talk about granularity. Then are we talking about bytes or cache lines? So there can be different things. Like in GPUs, we already can see that the cache coherency, if we still call it coherency, is maintained at byte level, right? Or at every 4 byte level. Then is achieved by write mask or dirty mask. Then for CPUs, we typically talk about coherency in cache line level. So if we're writing only 1 byte within this cache line, we're thinking we're updating the whole cache line. Okay, so this is the granularity difference in the CPU and GPU domain. Although there are still many different variations of like cache design that you can hybrid some CPU and GPU design decisions. That you can even do something like, oh, part of this cache line is valid, the other part of this cache line is not valid. These are also something that is totally possible in CPU design. Yeah, well, we talked about false sharing last time. So when different parts write different parts but considered as a conflict. So for example, this writes to the first half and this write to the second half, right? So this is called false sharing because the first one only needs 32 bytes. The second one needs 32 bytes. They're accessing different part of data. So there's no sharing. But if we consider at the granularity of a cache line, we have sharing. And if one side wants to write it, and if the other side also wants to write it, it's a conflict. Now we cannot make it to happen. How to prevent this thing to happen is to serialize them, to process one write first and process the other one. So this slows down the whole execution. It sometimes can be really bad because the communication between this cache and DRAM, can be really complex. Okay, so it can slow down the execution significantly, but for no benefit because the sharing are not real. We're not really sharing the data. It's only because we're using the cache line granularity. Okay, so to solve this type of cache coherency problem, we use cache coherency protocols. So I'll fix this coherency issue with complex mechanisms. So whenever we face some problem, we add one layer of indirection, we add more resources to solve this problem. Then there's always a discussion that if this complexity is worth the effort. And definitely, as we look at today's CPU architecture, you can almost find any consumer product that only has one core. Today, even cell phones have many cores, and coherency is always there. So in general, coherency is something that is necessary in today's design. So this complexity worth the effort, worth the difficulty, because of the benefit of multi-core system. So we start from a very simple coherency protocol. That is, we call it the VI protocol. Now, VI stands for valid. Whenever we say some coherency protocol, we use the state names to represent this coherency protocol name. So VI stands for valid and invalid. So here we talk about the bus assumption. What is a bus? Bus we talked about before. When we talk about digital design, a bus is basically a bundle of wires. They can say a data bus or address bus. It's a bundle of wires that are sending data or receiving data all together to represent one unit of data. Here, it's a little bit getting into the network domain or network on chip domain. So the bus has a slightly different definition, but not conflicting. So a bus is a unit. It's a set of wires, still a set of wires. It's still a set of wires, but can allow multiple senders or receivers. So when talking about, we're saying, oh, this cache unit and this cache unit can share this bus. Okay. When they can share this bus means there must be an arbiter. Arbiter decides who can use this bus in a cycle. So they first need to somehow communicate with the arbiter, say, oh, I have something to send. Then the arbiter say, oh, you send it. Then say, this cycle decided, send it, this side, send it. Okay, this is a bus. So bus is not a very efficient design because the communication must be serialized, right? In terms of like heavy traffic communication, like when there's a lot of traffic, they have to be serialized. So the bandwidth is limited. A better solution is auto connection, right? This cache to this memory, there's a connection. This cache to this memory, there's a connection. If this cache needs to talk, there's another connection. Okay, that's the best. But if we have an auto connection, then we need a lot of die size, a lot of wires, right? And a lot of energy. So that's a problem. So bus saves die size, saves energy at the cost of performance. But it's not always a bad thing. It's not always bad thing. So when we want to broadcast something, right? If we want to broadcast something from this cache to this memory and to the other caches, bus is very natural because all participants, everything that is connecting to this bus can overhear. Can basically, it's not the message is not intended for this cache, but this cache can still monitor what's going on in the cache and can still get a global understanding of what's going on. If you consider this is an auto connection, we need this cache to send to this memory and this cache to send this to this cache to achieve the same effect. Then that's less effective, less efficient. So there's always a trade-off between using a bus or not to use a bus. Then the general trend is not to use a bus. Not to use a bus for high performance designs and use a bus only for efficient systems. Okay, so here is a bus. Now for all the coherency protocols at this stage, we're talking about bus assumption. So whenever this cache sends a data to this memory, or this memory sends some data back to this cache, the other cache knows what's going on. Okay, and there's a way. It also assumes there's we allow peer-to-peer communication. So when you say peer cache, this cache and this cache, they are peers, right? Peer-to-peer communication is possible because it's a bus. If I just send onto the bus, then I don't care who is picking up the data. Okay, so let's look at different actions. We want to read the data. We read data, then we get the data ready. No problem. It's just as if it's a simple cache, right? Then we mark it as V state, as valid state. So it's a 1-bit flag. It's either V or I. But here, we just need to be careful. When we talk about cache coherency and cache organization, when we talk about cache organization, we say, oh, there's a cache line, right? A cache line has a major part that is the data. That is the largest part, right? We always have a tag, right? And we have a VI bit, right? So we say this cache line is valid or invalid. But that assumes that this tag is actually being stored in that cache, right? That's when we talk about cache organization. But when we talk about cache coherency, even if this cache line is not there at all, it's not in the cache. If it's not there at all, we say it's in invalid state. Okay. So all the cache lines that is in the memory, all the data in the memory, we consider they start with invalid state within the cache. Although it's much larger space, it requires much larger space. Okay. But anyway, when we read the data, we send the read to the memory, and data ready comes back. The data stored there, we mark it as valid. Okay. So as we draw a state diagram, we convert from an invalid state to a valid state. Then on the other side, we can do the same thing. Now, when the other side wants to read the data, we can get the data and in a V state. So there's a slightly design distinction, that a variation of VI's design. Do we allow V to coexist in two different places? Okay, they have pros and cons, but let's assume we allow that. V can stay at a different side. So if there are V and they can load data at the same time, okay, they can read the data at the same time, no problem, concurrency. So let's look at write. When we want to write data, what happens? We need to write to the bottom, right? So we're talking about write through cache for now. Because VI doesn't work for write back cache. We'll see why it's the case later. We write this to this V and we write to the bottom. Can we still allow this side to be in V state? No, we cannot, right? Because later on, if this V is still there, and what if the read happens on this side, right? If there's another read, we'll check, oh, it's valid, I can directly use it, and that's a wrong result. So we cannot allow this simple write-through design anymore. We have to have some other messages to notify something is happened. So what we call this? We call this as a processor write, PR write. I'll mark it later. You'll see other examples. On the other side, we are generating a bus write. Bus write means we're writing to the memory, and this write action is written into the bus. Okay, and this bus write is not only sending to the memory, and not only the memory is updating, and this bus write is also overheard by this cache, right? So this cache knows, oh, there's another bus write, right? There's another bus write. So I cannot hold it anymore. I just simply change my bit from 1 to 0, mark it as invalid. Don't use this data. This data is not valid anymore. Okay? So this is the simplest coherency traffic, although there's no extra traffic at this moment. Okay, so we're pretty much completed with a VI design. That's simple. So sometimes we also define a state transition diagram that we say different action in different state when different actions that are happening, what action we should do, right? And what state we need to transit into. If we're in V state, there's a problem. If we're in V state, when processor read the data, we just simply send the data back and we mark it still in V state. When there's I state and processor read it, it should not be no bus action. We should do a bus read, right? We read from the memory and we mark it as V state. When there's a PR write, when processor wants to write the data, then we can send it to V state and we send a bus write. In this case, we can do either way. This is depend on write policy. We can change stay at V state or change to I state, and it triggers a bus write. In this case, we know whenever there's a processor write, we have to write to the bottom. We have to notify other. We have to notify other L1 caches, other caches. There's a write. You have to invalidate, right? That's why VI protocol only works for write-through caches and impossible for write-back caches. Now for bus read, right? You need to be careful. These are bus read and bus write. Those are overheard data, overheard messages, where this cache is not the intended destination. I hear someone is reading the data, right? Here in this case, we say, oh, we're currently in V state and some other cache is reading this data. That's okay. We can keep it in V state, right? If we're in I state, we can actually, there is a chance that we can get back to V state, right? Because the data ready is also a broadcast. But in most of cases, we consider this is I state. It's not intended for me. Why I'm changing to V state? And if I'm changing to V state, that means we're actually changing another cache line to I state, right? Because if we want to put something into the memory, into a cache, we have to evict something from the cache. So for most of the time, although it's in theory it's possible to change to V state, we don't want to do it. We want to stay in I cache. Then in case of a bus write, say some other caches is writing into the memory, what we do is we change from V state to I state. We invalidate our own version so that later on, if we read it, we can fetch it from the memory. Okay, so this is a state transition diagram that describes all the possible communication cases, right? So also, this is called a snooping protocol. What is a snooping protocol? Snooping means you keep small something, you keep small something, that you keep getting this data. What is something that you're taking in? You're taking in what data is on the bus, right? So you keep hearing you're listening to the transactions on the bus and make your local decisions. Or in other cases, if this is not a bus, if this is other cases, the lower memory or this cache needs to initiate dedicated traffic to notify others. Say, I'm writing, you should evict. I'm writing, you should evict. It should go. It should this intentionally send this traffic to all other caches. Okay. So what's the snooping protocols really need to notify the other peers upon any action, depending on the protocol definition. It should need to broadcast some data. And for every cache, it needs to listen and to make the right decision. Okay. So Pro is generally low latency for small systems and is simpler design. And Con is poor scalability and traffic. Then if it's not a bus, then the traffic is huge, right? So what's on the contrary of snooping protocol, it's called directory protocol, a directory-based protocol. Then all the protocols we're talking about today can still have another version of directory-based protocol. So what's a directory-based protocol? Is basically this protocol is defined on the memory side. So not the protocol. Extra data is stored on the memory side. Say, the memory side need to keep a reference, say, oh, this cache has the data. and this cache doesn't really have the data, right? Then in that case, well, I send a write to this memory, then this memory knows, oh, if this part is a V state, I need to send this bus write to this cache, right? If this on this cache is a I state, I don't need to send it because I know it doesn't really have that part of data, right? Let me say again, the memory knows which cache has the data, right? So in this case, the memory knows, oh, there's a V and here's an I. The memory side needs to keep a directory to record all the cache status on every cache line. Now, in this case, we know there's only one V here, or there's a one V and there's another V later on, right? So whenever there's a write into this memory, we only need to send the cache that owns that cache line. It has a copy of that cache line, and only to invalidate on that part. There's no need to generate this traffic. So directory-based, as you can see, it requires much more overhead to record status, but can reduce traffic. So it works pretty particularly well when the connection is not a bus, it's like switches or even multi-layer of switches in complex systems. Okay, so this is snooping is the protocol and directory-based protocol. Now for VI protocol in particular, what's the pros and cons? So it's rather simple. It's the simplest design, only need 1 bit overhead. And I wouldn't say it's an overhead because you need to keep it a V and I anyway, right? Then, so it's minimal overhead in terms of state bit, and it's really simple. And cons is every write need to generate the broadcast. Just think about this pattern of read, modify, write, then read, modify, write. If I keep modifying one piece of data, it actually needs to generate a lot of traffic to the memory. And this is the same limitation as write-through cache. Right? For write-through cache, for every write, I have to write this data to the write every write, pass through this write to the memory, to the next level of cache for every transaction. It actually generates lots of extra redundant traffic. And so sometimes for simple, when people say, oh, what is the cache coherency protocol for GPUs? We sometimes still say it's a VI protocol because we need to mark V and I anyway, right, in GPUs. Still, I don't think it's an accurate description for GPU to say it's a VI protocol, because for GPU, there's really no need to broadcast this bus write to other for other L1 caches. If in GPU, if other L1 cache is in V state, it's okay. No, we just ignore it. If there's might be something wrong, it's a data race, right? It's a race condition that triggers a data race. Two cores are writing into one piece of data, where one core is write, one core is read. This is a data race condition. Now we may get some undefined behavior, and if we specify it's undefined and the result is really undefined, then it's totally okay. Okay, that's how GPU handles this. And let's make it slightly more complex. Let's see how this problem, these cons can somehow be solved by slightly more complex, and why did they use the protocol? Now I can tell you that in most of CPUs, VI protocol is not used because it's too simple and performance is not that good. And for CPUs, write back is a more reasonable a design rather than write through caches. Okay, so to solve this problem, we just make it slightly simple. We expand the V state into two states as M and I state. That stands for modified, shared, and invalid cache coherency protocol. Okay, for read, nothing special. We read the data, we get the data ready, we mark it as shared. Although it's not shared, we just mark it as shared state. Shared means at least it can be shared, can potentially be shared. Okay, we mark it as shared. Shared means it's clean. Okay, Clean means it has the same version as whatever in the memory. Okay. So share is clean, peer may hold it, and share may have another copy of the data. If on the other side I read it, then I generate a bus to read, I come back with the data ready that is in shared state. So I can write this type of representation. It's a slightly simplified table from different versions. It's not listing all the possible cases, but only the most useful cases. To have an event, the event is a PR read. Okay, the processor read. The processor is reading this data. And we only talk about miss. If it's a hit, it's not generating anything. The state before is I. We start from invalid state, and the bus action, we trigger a bus read. We read from the memory. Then the state after is shared. We change it to shared state. Okay, now what we do when there's a write operation, processor write, and assuming if there's an S and there's an S here, the question is, what state can we change to? And do we need to generate a bus write? So then the first question is rather easy, that we can change it to an M state, right? M means it's modified. Modified means it's dirty. And it doesn't allow any other cache to share it because it's dirty and only one cache line, only one copy can be dirty. Okay, now if we still keep this state unchanged, what if there's a read into this cache line? And it's the same problem as in the VI protocol. So we can consider S is a special case for V, right? As a special case for V, that if there's another read into read this cache line, we'll think it's valid and we'll return it, which is a mistake. In this case, we're considering, yes, we need a write to the next level, right? We need a bus write. But in fact, what we actually need to send is to notify onto the bus, say, there's a read, there's a write, right? So, but let's assume these caches are write back caches. If these caches are write back caches, by definition, we shouldn't write back. We shouldn't write to the memory. Writing to the memory is slow. We don't want to write into the memory. So the solution is, rather than generating a bus write operation, we just create another traffic message type. We call it bus read X. Okay, so what does bus read X do? It means we say no to other read, right? If I say, okay, bus read X, all other places, all other caches don't read from here. We exclusive read, right? We don't want the read to happen. In this case, whenever this cache receives a bus read X, we mark it into I state. We don't allow it to be in the S state. Okay, we mark it to be I. So this M state to be the solo owner of this cache line. Okay. Now we mark it into M state. When on in cache write, and we also change from S state to the invalid state. I should add an arrow here. From S state to I state when the event is a bus read X. So it's a different type of event that we've never seen before. So whenever it's a processor write, it starts from a shared state. We generate a bus read X and convert to the M state. Okay, so bus read X is less expensive than a bus write because the next level of memory is slow. Okay, so what if we have, in this case, we have a write again in M state? If we're in M state and there's a processor write, we want to write into this piece of data, we know we're the solo owner and we know we're dirty, then changing to even dirty is still dirty. So it's okay, just write it locally, write into it, and don't generate any bus traffic. As you can see, if we keep modifying one piece of data, it can actually save a lot of traffic because we don't need write through, we don't need to generate the bus write, and we don't even need to generate bus read X operation. Okay. It's the advantage over the VI protocol. We reduce bus write traffic. Okay. Another case, what if we want to read into I? We already talked about read into I. We know it's going to X, but this is a slightly more complex situation because we have a modified version on another cache. Bus, right? Yeah. Yeah. So that's, then you predict my question. So we want a bus read, right? And eventually it will send the data ready. But this one can be overheard by this one. So is there any problem with this design? First, yeah. So in this case, memory has V1. We eventually want here to have V2. This one already has V2. We eventually want this one to have V2. So this is a wrong design because we're still reading V1, right? So we have to read V2. How to write V2? It's basically by generating another bus write. And we can either change it to S state or I state here. Now, in this case, we mark it as shared. Okay. So you can consider this is a rather complex behavior and definitely a multi-cycle thing. So just ignore any network traffic, not network traffic, network latency. Consider everything can be completed. Every transfer can happen in one cycle. What is actually happening is we're generating a bus read, right? We need to wait one cycle for my peers to say, oh, I have the data. And I have to wait one cycle. If there's a latency, that's more than one cycle. But in this case, we have one cycle. And if you consider wire designs or network design, what wires are actually needed at this moment? In this case, this is one cache line, right? This is one cache, and this is another cache. So other than this read write transaction theories, I will draw it this way. This is working, writing into the bus anyway. So other than this regular read and write data, buses, we need at least for here, we need an for wire that's saying I have data, right? So when this one triggers a bus read onto the bus, this is what happened in cycle 1. In cycle 2, this one needs to respond. Say, in 1 is I have the data. Then, or in 0 is I don't have the data. If it responds with 0, then in the third cycle, say suppose 0, right? In the third cycle, this can go back. Data ready can go back, right? In case if this one is saying 1, right? It may wait extra process, or say in the third process. I don't even want to say this is third cycle. It's not likely to be complete in 3 cycles. That this is a write back, right? It's a write back and evict. And in this case, this happens as the 4th stage. And this control is actually can be quite complex, right? If you consider something like during this process, there's a read comes in. How we can handle this type of cases, right? And during this process, there's another read that comes in here. So It just make this type of design super complex. The simplest way is when there's a read and whenever this one like detects is some of these state needs to go onto a transient state, temporary state. So the temporary state blocks all the read actions. Okay, something like this. So it can be really complex. And if you go down to the simulator level or into the microarchitecture level, it's not only about 3 states. There are many transient states that can happen to prevent all the corner cases and to guarantee that there's no corner cases that you have never thought about. It is really, really complex. It's need long focus and consider all different cases and to really have a clear mind so that you can design this type of system. Okay, in this case, anyway, we have a bus read and it triggers a bus write, and then the data ready come back from the L2 cache. Okay. So what's the pro, or at least what problem is MESI solves over VI protocols? It reduces write traffic, right? Because we can support write back cache, and it supports 30 tracking. So we know with 30 tracking, if we need to write one piece of data, then again and again we're still saving write traffic. Then, but what are the cons? In this case, I'm slightly modifying the previous example. In the previous example, they both are in S state, right? But what if I slightly change it? Say there's a write and this is an I state. What do we need to do? Ideally, we want to do nothing, right? But can we really do nothing? Because just you need to turn on the fog of the war, right? So you need to consider what information you have available. Well, you can see from the bird's eye view, you know everything. You know this has I state, but when we make a decision, you should consider this cache as an agent itself. It only has the information that is available to this cache. This agent or this cache unit knows I'm in S state. If I'm in S state, that means it's shared. Other cache can hold it. So I don't have the information that other caches do not hold it, right? So the quick answer is I still need to generate the baud read X. I still need to wait for this one to tell me, oh, I don't have it, right? I don't have it, then this one goes, no. This one still need this one to say, I don't have it. I don't need to do anything. Then this write can happen. Okay, so at least the limitation, I don't say it's a con. When you say pro and con, you need to say what you're comparing against. The limitation is we have this unnecessary invalidation. And this can happen actually a lot. Why? Because very likely you have one thread, one program running in one core, another core running another thread, and they're running totally different data. So exclusively owned by this cache line is very common in CPU execution, right? See how likely you are running single core programs. Very, very likely. Lots of programs are written in a single core design. If you, for every write, it's not in modified state. For every write, you need to send a bus invalidation, how much extra traffic you are generating, right? So this is a big penalty for performance.